My name is Szymon Karpiński. I work at NVIDIA. It's really great to be here on EuroPython. I come from more like C++ background, so it's my first Python conference, and I really enjoy the community, all the talks, all the hallway discussions. So it's great to be here, and thank you for that. And now it's my time to give a talk. I will talk about how at NVIDIA we try to bridge the gap between C++ and Python in terms of GPU performance. Specifically, I'd like to talk about our new, 1-year-old, but still new, open source library called nvmath-python that we're building at NVIDIA and which aims to deliver peak performance of math libraries to Python world. So in this talk, I will cover 3 main topics. First of all, I'd like to tell you what nvmath-python is and what it isn't, and why you should use it, and maybe why you shouldn't. Then I'll dig a bit deeper into the internals to show you how it works on the inside, how the layers which bridge the way from C++ to Python look like. And finally, I talk about challenges of bringing GPU performance to Python. We see different kinds of challenges in our work. It's non-obvious. I believe that some of those challenges are unique and some are universal. So I hope this part will be interesting for you as well. So let me start by describing nvmath-python, or maybe let me even back up a bit to describe NVIDIA's software stack, how it looks like. At the bottom of the stack, there is the GPU, of course. This is what we make. We sell GPUs. That's the key product, but nobody buys GPUs just to have GPUs, right? At least I hope so. I hope that people buy the GPUs to do meaningful work on them. We hope they use GPUs to accelerate their work, to make their lives easier, to make their computations faster. And GPU on its own does not really have the power to do that for many people. You need some layers to allow people to use the GPU. So there comes CUDA. CUDA is a programming framework which allows people to write their own programs for the GPUs. CUDA is a unified framework that does an amazing job abstracting away the hardware differences between generations of the GPU, but still it's not possible to abstract away the hardware completely. For those of you who tried CUDA, you know that it's not an obvious language to write in because you still need to think about the hardware that is underneath. So while this gives people some possibility to accelerate workloads, it's often not enough. People expect some higher level building blocks. So we have CUDA-X libraries. CUDA-X libraries is a set of hundreds of libraries that we've created to accelerate every workload, every industry. We have a whole range of library that covers various domains. We have quantum simulation libraries, chemistry, lithography, data science, computer vision. We have a library that accelerates almost everything as a building block for people to accelerate their specific workloads. And in the middle of that CUDA-X libraries are CUDA-X math libraries. This is what my team works on. We deliver libraries that perform fundamental mathematical operations on the GPU in an accelerated way, aiming to achieve peak performance. So there is cuBLAS. cuBLAS is accelerated linear algebra library for matrix multiplications and similar operations. We have QFFT for fast Fourier transform. We have sparse solvers, and in general, a set of libraries that aim to accelerate fundamental mathematical operations. Those libraries are later on used by higher level libraries, for example, QDNN for neural networks. So the question is, those are C++ libraries, those math libraries, and how do we bring them to Python? So what we try to do is to expose the power of those libraries to Python. So math libraries are already exposed to Python, for example, via Torch or CuPy. Those libraries use math libraries underneath as their backend. So whenever you train a model in Torch, it uses, for example, cuBLAS underneath to do the matrix multiplications on the GPUs. But they only expose part of the functionality of the libraries. The advanced features are not exposed. Those math libraries have advanced fine-tuning features that allow people to get peak performance, such as support for narrow precision, some numerical settings which allow you to find a trade-off between performance and precision for your specific use case. They have some fine-tuning options and lots of knobs that you can tweak, which are not really exposed to Python because existing libraries abstract away all those things to provide a unified, simplified experience for the user. So if you are a library developer or an advanced user who wants to access those advanced features because you want to fine-tune your workload, you have a hard choice. You need to choose between performance and ease of use. You can either go to C++ and access those libraries directly, or you can agree to use the simplified general API of existing libraries, which is definitely much easier to use, as you can see by the amount of code on the slides. But we thought, why not both? Is it really impossible to combine those two worlds? So this is what nvmath-python is. nvmath-python attempts to expose all knobs, options, preferences, settings of the underlying CUDA math libraries to Python. And we don't try to compete with existing libraries such as CuPy or Torch. They are great. They are standard part of the ecosystem, I would say. So in fact, we don't even have our own tensor type. If you give us torch tensor, we'll perform the operation on torch tensor and give you back torch tensor. If you give us CuPy array, we'll do the same on CuPy array and give it back to you as a CuPy array. So we try to fill the gaps that the libraries have and not replace them. So our goal is to maintain ease of use known from those other libraries while still exposing full capabilities of the libraries underneath. So in nvmath-python, simple things are simple. If you want to just multiply matrices, it's as simple as it is in any other library. What's different is that you have access to all the options of the underlying library. So for example, you can ask kublas to perform a fused ReLU epilogue after your computation. And this is high-performance kernel with ReLU fused, so it's much faster than any other ReLU implementation that you can perform on your own. And this is what kublas provides, and we just bring it to Python. Or you can compute in narrow precisions with full control over quantization and dequantization to make things more memory efficient. And this is also a capability of kublas that we try to bring to Python. And recently, in the release of nvmath-python, we've added support for QDSS, which is direct sparse solver. So you can now solve sparse equation systems on the GPU using QDSS in a similar fashion. If you want to just solve them, just import solve from nvmath-python and type solve, and it solves the equation. But if you want to access all those fine-tuning possibilities that are there in QDSS, you are free to do so. You have all options exposed to you to Python. In addition to this classic interface, we offer bindings for Numba. So if you happen to write a Numba kernel that is JIT compiled to CUDA using the Numba CUDA, you can use math libraries from within that kernel. This is then runtime compiled and JITed together so that this computation becomes an integral part of your kernel in Numba. So that's another thing that we offer, an integration with Numba. And recently, we also started adding support for distributed computing. So if you have more than one GPU, if you have hundreds of GPUs, you can scale your computations using libraries such as QFFT-MP with distributed computing capabilities using quite a simple Python code. I'll talk more about distributed computing and its Pythonicity later on. We're also planning to add support for cuBLAS-MP, which is distributed equivalent of cuBLAS, so linear algebra on multiple GPUs. So this is how nvmath-python, what nvmath-python does, and now let me tell you a bit about what's inside nvmath-python to give you an overview of the architecture that we have. On top of the CUDA-X math libraries, which are those C++ libraries, we have a thin layer of auto-generated one-to-one Cython bindings. One-to-one means that every single function is exposed in those bindings. So you have a layer of Cython that maps every single function in those CUDA math libraries to Python. And the cool thing about this layer is that it's public. So it's not just an implementation detail of nvmath-python, it's our public API. So if you don't really want to use those higher level APIs, you can just get our bindings and build your application on top of that. And then you don't need to write the bindings yourself. And on top of that, we have 3 different flavors of APIs. We have host APIs, which are the first ones that I've shown to you. Those allow you to call GPU from host code, just as you do with CuPy and storage, but with access to all those advanced features. We also offer integration with a feature of QFFT called LTO callbacks. LTO stands for link time optimization, and this feature allows you to write custom prologue or epilogue in Numba, which is a pre-computation or post-computation step, and it is then JITted together with the actual FFT so that you get a fused kernel with your custom prologue and epilogue, which in many cases which involve FFT makes things much faster and smoother. And finally, we have device APIs. The device APIs are those that allow you to run math libraries from within Numba code. And this happens thanks to our runtime compiler stack. So nvjitlink and nvrtc are there to compile the actual computation together with your Numba code. And in the middle of that is CUDA core, a silent hero, I would say. It's a standalone library which is separate from nvmath-python, which what it does, it brings CUDA runtime to Python, not just by binding it, but by exposing it in a Pythonic manner. So things like device management, stream management are handled by CUDA core. It's a super useful library if you do anything with GPU and Python and you want to get more control and you don't want to get to lower level. So CUDA core abstracts that away. So this is how it looks on the inside. And now let me talk about a bit about challenges that we face. Faced and face. It is still a library in development, so those challenges are still there. So the first challenge that we face is the interoperability challenge. On one side of nvmath-python, there is a diverse ecosystem of different tensor libraries, such as Torch, NumPy, CuPy. They have common patterns, but they have slight differences. They have own abstractions. They use different memory spaces. And on the other hand are the C++ math libraries, which also have their own way of seeing the world. They think about data as pointers mostly, and they have certain requirements, both in terms of the input, and some operations are supported, some are not. So we need to somehow connect those two worlds in terms of technical interoperability. But it's not only about interfaces. It's also about different ways of thinking in those two worlds. Python way of thinking is mostly about abstracting. That's why Python is so powerful. When you see a NumPy array, it's an array. You think about it as a multidimensional object, and that's it. You don't really need to care about things like how it looks in the memory. On the other hand, there is C++ way of thinking, which is much less abstract and much more verbose. So C++ basically thinks about tensors just as flat memory, maybe with some metadata added that makes it interpretable as tensor data. So it's not only about connecting those two worlds in terms of technical changes and differences, but it's also, and maybe even more, about connecting two distinct ways of thinking. So to deal with the technical differences between the libraries, we tried to add another internal abstraction for the tensor. So we view all the tensors through a shared common view that dispatches the operations on the tensors to respective libraries. And we have abstractions for streams, etc., to just cover those differences between libraries. But in terms of these conceptual differences between C++ and Python, what we try to do is to absorb as much complexity as possible ourselves so that the user doesn't need to care about that anymore. So we do it once, and then we hope that the user won't face the same problems that we did. So we try to help the user get it right. The libraries have some requirements, and if it's possible, we try to adjust the inputs from the user to match what the library expects. And if it's not possible, we try to raise a helpful error, where helpful is also tricky, because the way the C++ library sees a problem is rarely corresponding to what happened in Python. And the errors from C++ libraries are rarely actionable for Python users. So we try to translate the problems and then they tell the user in Python terms what went wrong and what can be done to fix it. So it's less technical, but more UX effort. And in general, we try to map users' way of thinking about problems to the way that libraries see it. And we constantly try to improve this part of nvmath-python to make the Python users feel as friendly as possible. Another challenge comes from a design decision, which is to use as much Python as possible. We, compared to other libraries, have quite a thick layer of Python, while others usually go to Cython or C++ layer pretty quickly. We believe that having more Python means more hackability and extensibility for the users, that it makes the library more friendly, and this adds some overhead. And this doesn't usually matter as you schedule huge workloads on the GPU. However, with fast enough GPU or small enough problem, an overhead always matters. And we try to eliminate it in two ways. We have what we call stateful APIs. So instead of just multiplying matrices, we give the user a possibility to plan the operation once using a plan call, and then execute it multiple times or multiple data in an iterative process, for example, without need to replan. Because planning usually depends on shapes, types, and not the data that is there. So this, in case of repeated computation, amortizes the cost that we see. Also, we try to make execute as thin as possible. We try to do as little as possible there, because most of the heavy lifting can be done in plan, so we try to make execute thinner. And I believe that what I've learned in many performance talks in this conference will help me optimize this bare minimum of execute to run even faster. So I hope to use the knowledge that I've learned here to make the overhead even smaller. And finally, another challenge that we faced is the distributed memory management. As I mentioned in the beginning, we've added support for distributed memory. So we use QFFT-MP to perform distributed FFTs. In distributed computing, as the name suggests, data is distributed among nodes. So every node holds a part of the problem, part of the input tensor, for example, in its memory. And we use nvshmem as our memory backend. This is what QFFT uses. And in nvshmem, allocations are collectives. Collective operations mean that all nodes need to come together to perform that operation. So when each node wants to allocate a part of the memory for a part of the problem, those nodes need to come together and do it in the same order and in the same time. It's not possible for one node to allocate without another node allocating at the same time. So this means that we can't really rely on any implicit memory management system because they are not predictable enough, and we need to figure out a way to make those nodes allocate and free memory at the same time. And for us, this means that we need explicit allocations and free, which are definitely not Pythonic, and we kind of regret that, but we don't really see another way to go around this limitation of distributed computing. But we did our best to make it as friendly as possible despite the explicit memory management. So we figured out that after all, a tensor, an array, is just a pointer plus some metadata, which means that any memory can be wrapped into torch tensor or array. And instead of just returning some raw memory from this allocation that can be only used by us, we wrap this memory into a framework. So when allocating the memory, user can pass name of the framework that they use, and we'll allocate memory from nvshmem pool, which will be proper distributed memory, but then we'll wrap this memory into a tensor. So what the user gets looks like a tensor and behaves like a tensor. They can make modifications to the local chunk of the memory using just the tensor API, which makes it possible to combine distributed and non-distributed computations in an easy way. and makes this distributed memory, despite being allocated explicitly, interoperable with other frameworks and other libraries. So we hope that by doing that, we can improve user experience just a little bit. So these are the 3 challenges that I think are key in nvmath-python. I presented the solutions that we have, and I'm open to any discussion about how it can be made better. And in the end of this presentation, I'd like to wish nvmath-python a happy birthday. It's our first birthday. We released beta 1 for CuPy 2024. Since then, we had been constantly developing. Our 5th release was for CuPy 2025, just 8 days ago, I think. So in this last release, we added support for QDSS. And we plan to constantly develop the library to accommodate as many NVIDIA math libraries as possible and to bring full power of those to the Python world. So if you would like to give nvmath-python a try, here's a QR code and a link that will redirect you to our product page. There is the documentation, there is a link to our GitHub. So going back to the original question, what is nvmath-python and why you should use it? If you are okay with the current performance of your workloads, then I guess you're fine using existing libraries. But if you want to make it faster, or you just want to experiment to see how much faster it can be made, just out of curiosity to explore what possibilities the underlying libraries offer, I strongly encourage you to give it a try. And if you have any issues or feedback, please reach out to us on our GitHub or to me personally, and we'll keep improving the nvmath-python until we reach our first non-beta release, which will hopefully empower Python users to get great performance of the GPUs in Python while not compromising ease of use. Thank you very much.
Thank you very much, Szymon. So are there any questions in the audience? If not, my question maybe...
There's a question.
Is there? Oh, perfect. Go ahead.
Okay. So this is a really simple one. Maybe you could talk a little bit about your... sorry, great talk, by the way. I really enjoyed it. Thank you so much. Maybe talk a bit about your plans and hopes for free threading in nvmath-python. I guess there seems to be a lot of overlap.
Yeah, free threading is an important topic. In our case, most of the heavy lifting happens in the C++ libraries, so we are not that much affected by GIL or lack of it, because after this thin Python layer, we redirect the computation to the C++ library, and we, of course, make sure to release the GIL for that time. But free threading will definitely make GPU computing easier, because it will allow you to use multi-threading for the rest. So while we are not directly affected by free-threading Python, we hope that introduction of free-threading Python, which increase the usage of GPU computing in Python. So we keep our fingers crossed for that effort, because it makes lots of things on the GPU easier, and we hope to see increased adoption once this becomes the mainstream.
Awesome. Thank you so much.
Thank you.
Is there another question? Okay, so then I will ask then. You mentioned that you are supporting PyTorch or NumPy. If, for example, I'm a JAX user, can I also benefit somewhat from your...
Not yet, but supporting JAX is on our roadmap. So any framework that would benefit from math libraries exposed this way, we plan to introduce it. But JAX is not there yet, but will be. That's what I can promise.
Thank you.
Hey, I'm one of the Pyro contributors, and I'm just wondering whether you did enable data interchange with Arrow, and if not, let's talk offline.
Sorry, can you repeat?
PyArrow, are you familiar with the project?
Not yet, but...
Apache Arrow. Okay, let's talk offline.
Yeah, I'm sorry, I'm quite new to Python world. I mean, I'm from the bottom of the stack, so I'm happy to talk and learn more about the project.
Sure.
But sorry, I'm not familiar with it.
Perfect, thank you.
Thanks.
Okay, is there another question? If not, then please give another round of applause to Szymon.